This is lecture 21. This is going to be introduction to experiment 8 and also an introduction to lookup tables, which is used in experiment 8. Not a big deal, fairly easy concept, very useful. So this is the state diagram representing the control unit state machine, and what we're interested in here is the signal, the conditioning of the interrupt signal that connects to the microcontroller. So what we're concerned with is if that pulse is too short, the state machine up here is going to miss that. If that pulse is too long, it may have multiple interrupts processed for the same asserted interrupt signal. And so we don't want that either. So the other issue we want to deal with is when we connect the interrupt to a switch or a button, it has mechanical bounce issues, and we don't want that to affect the operation of a microcontroller. And like we said before, if there's bounce, each one of those bounces may generate an interrupt in and of themselves, and that's typically not what we want. The issue with microcontrollers is the fact that they're very fast. Everything happens on like the nanosecond level, and so we gotta be able to still interface with mechanical switches like switches and buttons. And so one of the issues here is bouncing. A bouncing button here is going to cause multiple interrupts and other problems. And essentially, we can fix that with either in hardware or software with a debouncer. So for this experiment, we're going to do a hardware debouncer. Also, we have the issue of the interrupt signal being too short or too long. We're going to fix that with another piece of hardware that we call one-shot. So this is the debounce hardware diagram here. Once again, these are provided for you. Essentially, here's the signal comes in like this, and it comes out like this. For example, if that's a positive going pulse, and there's a delay time right here where it can be bouncing, and those bounces are ignored for a certain amount of time. And so it's essentially what it's waiting for is to arrive at the steady state before it outputs the value. And so that's our debounce mechanism. Typically this delay here is configurable essentially in the hardware we're providing. It is a parameter in the model, and you can instantiate it with any length pulse you want. The other issue here is a one-shot. So we have a one-shot here. What we're going to do is take the output of this signal, essentially connect it to the one-shot, and that's going to make sure that all it's going to do is act on that edge there. When it sees that edge, it's going to send out a pulse. This is your positive pulse, or it could send out a negative pulse. It's actually set up to do both. You can choose which one you want. So essentially this pulse width here is important for microcontrollers. Once again, it can't be too short or too long. And I think we agreed upon that it needs to be at least 3 clock cycles, and it has to be less than 8 clock cycles. So the ideal length is 3 clock cycles, which guarantees it's always going to be the interrupt. If it comes in, it's always going to be caught by the microcontroller. So here, once again, this is what you think your switch looks like. It's actually causing some type of bounce like this. Each of these bounces could be an interrupt in and of themselves, because this bouncing here is on the millisecond level. And so what ends up, the signal being debounced, it looks like this, so essentially there's this delay, and then we're going to feed that into a one-shot. The result is going to be this signal here, and this once again, this pulse width is configurable via a parameter in the hardware we're going to provide. So experiment 8, it's fairly simple in practice. So essentially, it's going to count the number of button presses. So on the board, you're going to be pressing the button, and it's going to count that the program is going to count those and display it on the 7-segment display. So what we're going to do here is we're going to use a button count of We're just going to do a 2-digit button count. So you have to multiplex the displays to handle 2 digits. So more on that later. And so essentially we're going to, anytime you're working with a button, we're going to both debounce it and one-shot it. Okay, so but the hardware is provided for the debounce and one-shot, so you don't have to worry about that. So the way this works is the button is connected through these 2 devices up to the interrupt pin. So essentially what's going to happen is you press a button, it's going to generate an interrupt, and you're going to count the number of interrupts. So the big requirement in here is to count the number of interrupts using, so that means you have to multiplex the displays in firmware, but the requirement here is to use a lookup table based approach, and we'll get to that in a second. So multiplexing displays, hopefully this is something you went through in your previous digital design class. And this is 4 7-segment displays. This is what's on the Basis 3 development board. And so the idea is that these there's 32 LEDs there, but they're actually controlled with 12 signals. And the way it's controlled is so these are all the A segments. They are all shorted together. So I can't ever turn just one A segment on. If I want this A segment on, I turn on this anode and I turn on all the A segments. Okay, so the issue is that with that kind of model, I can only ever display one number at a time on this display. So this display, it can display as many numbers as you want so long as they're the same number, but at any given time I can only display one unique number. So what I'm going to do here is display that for a while, wait, then display that, then wait, then display that, then wait, then display that, then wait. Okay, so I'm only displaying one at a time, but if I do it fast enough, it takes advantage of persistence of vision or retinal persistence, and it makes it look like there are multiple numbers on the display at the same time. So there's a couple issues here. Generally speaking, if you try to multiplex this too fast, you're going to get some ghosting problems. If you multiplex it too slow, you're going to get flicker. Either way, your eyes are not going to enjoy that. So this is the algorithm to use to multiplex the displays. Remember, I have 2 things out there. I have the anodes, which is essentially a switch, and the cathodes, which are the segments. So the first thing I want to do is turn everything off, turn all the displays off, and then I want to write my data, the 7-segment display data. I want to write that to the output registers, and then I want to turn on the appropriate display. I'm only going to turn one of those displays on, and then I'm going to wait. Okay, so this delay, if I don't do this delay here, the numbers will be dim and they'll be kind of ghosting. So this is, I think there's a delay in the experiment write-up. It's just a short FF type delay, not a big deal. It's not a super critical time thing here. The issue is that because part of the time you have everything turned off, it's going to affect the display. So what you want to do is turn everything on and then wait such that the time that things are on is much greater than the time that things are off. Okay, so I'm going to do this for both the tens digit and I'm going to do that for the ones digit. So I'm going to display one digit, switch the other one, switch the other one, switch the other one, back and forth, and that is going to be my display routine. So essentially I can put an arrow around the back on that thing if you want. So this is real important, not a big deal. It's not overly complicated. Follow this algorithm for both the tens and ones digits. So these are some of the problems you can have when you're multiplexing displays. So if the displays are dim, that means they are off for too great of a percentage of a time. And essentially there are a couple of issues here. Either your delay is not long enough, or the multiplexing clock is too fast. So slow the clock down, give yourself a delay. Second thing here is it can ghost, which means it has these little dim segments lit up, and that can be from two things. Once again, too fast to the clock. Also, if you have the wrong data on the wrong display at the wrong time, it is going to appear like a very dim display. So you got to fix your algorithm in this case. And lastly, if it's flickering, it's just too slow, you got to fix the multiplex clock, however you're multiplexing here. And essentially, this is the same thing here, in that the opposite of that thing. If it's flickering, the delay is too big, speed the clock up. So you have to keep track of a count in experiment 8, and there's two ways to do it. There's no super easy way to do it. You have to do all the grunt work yourself, and that's the key. So essentially, experiment 8, you are required to count up to 49, I think, which means 2 digits. And so there's two things you can do. The best thing to do is you could keep a binary count and convert that binary count into like a BCD or a decimal count every time you want to display it. But the easiest way is to keep a register for the ones data and a different register for the tens data. So when you get an interrupt, that means someone pressed a button. That means you want to increment the count, which means you increment the ones count. Okay, so this is a typical BCD type algorithm where you increment the ones count and then you check it. If the ones count is 10, that means you went from 9 to 10, which is greater than 0 through 9. So what you're going to do is subtract 10 from the ones count and add 1 to the tens count. And that's basically the algorithm you're going to use in this experiment. So in this experiment, what you want to do is it has in the debouncer and the one shot. Don't touch your microcontroller. Put those two modules on the wrapper level. So when you're implementing this experiment, the best way to do this is to hard code some count values into a register like 34. Make sure they're different numbers, and then make sure you can see those numbers on the display. That means your display multiplexing algorithm is working right. So these two registers here are one for the tens count and one for the ones count. So lastly, when that's working, then you could work on the interrupts, which is the foreground task. So the best way to do this is first to verify you get an interrupt, and that means inside your interrupt service routine you should turn on a known LED and then kill your program by just jumping to the same instruction over and over again. If you get that, that's great. Next thing you can do is just take that out. Typically speaking, the best way to do this program is to put the count massaging, the BCD decimal, add 1, blah blah blah, put that in the interrupt service routine. It makes everything really easy in this experiment. Lastly, when you're doing this experiment, don't forget to re-enable the interrupts. Okay, so once summary here, get your display multiplexing working, background task, and then work on your foreground task, which is to verify you're able to get an interrupt. So that's the experiment. The experiment does require you to use a lookup table. So lookup tables are super important in digital design and programming. They're generally a kind of a fast way to do something. They do represent a trade-off of sorts. Essentially, it requires more memory, but in the end, it's faster. So it's up to you to decide what you need to do on this thing. So it's nothing new. It's very similar to arrays and higher level programming. Also in digital design, we called generic decoders were essentially lookup tables. We use them quite often. And yes, it's relatively simple. Like I said, I think you've done this before. Just don't freak out by it, and Just know what you're doing. There are some tricks that we have to deal with on this thing. And I'm going to go through this with an example problem. And this is the example problem, but one more thing to say before that is let's essentially, we know that the memory is a higher level form of memory, which means it's a little bit slower. Registers are fast, of course, but the problem is registers, the registers being used are fixed at assemble time. So essentially you can't change these registers when the program's executing. So it always accesses X3 in this example. So typically, it's great when you need to, but it's always not what we want. So a more generic way to do any type of programming is to work with addresses. So essentially we're going to put addresses into registers and use those to access memory, and we can do so in a super generic way. Have you seen with many of the programs we've done here, it goes to memory and it uses a register as a memory address. You've seen this before. It's really a generic way to program, not as fast as registers, but simply the genericity makes it a better choice in many cases. So the problem we're going to do is calculate parity. So we calculated parity before, and what we're going to do is calculate it using a lookup table, and then we're going to compare the operating speeds of these lookup tables. And what you'll see here is that there is a trade-off. One program is going to be longer, but it's going to operate faster. So we'll get to that inside the example problems for this set of lectures. So we're going to call this done for now.